Hello, everyone. Welcome to chapter 13 of the deep learning course. Those who have been following where we are in our study this semester, first 12 chapters was about deep learning practice, and the remainder, some 4 or 5 chapters remaining, are about deep learning research. So this is the first of the chapters on deep learning research. Sounds like a familiar topic. Linear factor models is the title of this chapter. So uh, we're gonna begin with how data, very high dimensional data, such as a large number of images of some topic, like celebrities' faces, or cats, or dogs, or what have you, how they all lie on some lower dimensional space. And once you find that, it saves you a lot of trouble. One of the troubles with very high dimensional data is what's called as the curse of dimensionality. So we overcome the curse of dimensionality. And also we find out what is the essential representation that is needed. So it's kind of interesting topic. But it's related to a number of topics. You might say, well, I know about this and that. I know about principal components analysis. I know about factor analysis. So this kind of ties everything together, saying what are all these methods? And what is the deep learning take on this? So that's what we're going to do. So in the lecture, we're going to begin with an image of a particular galaxy in space. It's kind of interesting photograph. I have a friend who's an amateur astronomer. He's actually in one of the other engineering disciplines, but after retirement, he's taken up photography. So he has got a camera in his backyard, and he regularly takes fantastic pictures of all kinds of celestial things. So he directed his camera at a particular constellation called the Andromeda constellation. And through the constellation, you can see a galaxy. And that particular galaxy has a name. It's called M31 is the name of the galaxy. And he has taken a nice sharp picture of the M31 galaxy. And apparently M31 galaxy is the galaxy that is the closest to the Milky Way, right? You know that the Earth and the solar system is all part of the Milky Way galaxy. And the M31 is the closest galaxy. It is about 2.1 million light years away. And apparently this particular galaxy is heading towards the Milky Way. So it's going to start approaching the Milky Way. In about 4 billion years, it's going to reach the Milky Way. And it's going to cause a catastrophe. Is it two galaxies hitting each other? But it turns out that within a galaxy, the stars are all very far apart. So apparently it won't cause much of a conflict in our Milky Way and the M31. They'll just go past each other. So anyway, it's rather fascinating to hear about astronomy. But what was interesting to me was when I looked at the nature of this M31 galaxy, it looks like a flat pancake within three-dimensional space. You know, the stars and galaxies, they all have all of three-dimensional space to, you know, have all their stars distributed. But no, it has chosen a flat pancake. So there is only a pancake. The stars are largely on it. Not that every one of them is on a pancake, but mostly on a pancake. And if you think about it, even the solar system in which our Earth is located, the various planets that go around the sun, they're not orbiting like, you know, every which way, like we see pictures of atoms and protons and neutrons. They're all flying all around with different orbits. No, not the solar system. The solar system is all on a pancake. They're all on the same plane and their orbits are on the same plane to a large extent. There's some variability. Like Pluto is off by 7 degrees or something, and another planet is off by a little bit, but very small. So they all move around in a pancake. Although they have all of three-dimensional space to have created their different orbits, they're all on a flat pancake. So why is that? Why is the solar system on a planet, and why is the M31 galaxy, entire galaxy, is on a pancake? It's got something to do with centrifugal forces and so on, physics and the gases and things like that, which ends up in a pancake. Well, here in machine learning, data analysis, data science, deep learning, we're not talking about physical planets. We're talking about data. Like we think of, an image as a point in a high dimensional space, like a celebrity's face. It's just a point in a very high dimensional, million dimensional space corresponding to all the pixels. And we look at faces of other celebrities, and okay, there are different points. Well, they could lie on any anywhere in the million dimensional space. But it turns out they also lie on a pancake. They don't lie anywhere. And again, why is that? It's got nothing to do with physics. It's got to do with the nature of data. So the faces have a certain constrictions about, the eyes and the nose and the ear and so on. So there are all these standard things about faces. So one face is not that different from another face. Maybe they're quite different looking, but it's not going to be moving you totally away in that multidimensional space. So all the faces that you can think of are all going to be lying on near each other, and you can move from one face to the next face, change the eye a little bit or change the nose a little bit and so on. So there is an interesting analogy here between the physics of the stars and the nature of objects. They all form pancakes. So the question then is, how do we find these pancakes, and why do we want to find these pancakes? And the reason to find these pancakes is it's going to be in a much lower dimensional space than in the million dimensional space. If it's a 1 megapixel image, it's a million dimensional space. So we don't want to be dealing with that many. So we are dealing with a smaller number. And so whatever we want to do, the faces, recognize faces, or in the idea of going from one face to the next face, what are some nearby similar looking faces? Or what about creating a brand new celebrity face? And you might have seen some pictures of non-existing celebrities. They look like celebrities, but they don't exist. They just moved around on the pancake to find another point, and there's going to be another face, and as good as any of the other faces you have captured with the million pixel resolution. So it is this topic we're going to be exploring, okay? And what we're going to do is we'll first explore the idea of a simple idea called principal components analysis. You might have heard that. You might have taken an introductory course on pattern recognition or statistics or even linear algebra, where they teach principal components analysis, which says if you have data in a multidimensional space, we can ask to find what are the directions in which most of the data is concentrated in. So it has got the highest amount of variance. So find the direction in this three-dimensional space, or even 4 or 5 or whatever number. Find me the direction in which the data is most spread out. In some directions it might not be much spread out at all. In others it might be more. Find me the one in the highest direction, and we take the orthogonal direction to that and say, well, here are the directions along which the data seems to be spreading most interestingly. And those directions are referred to as the principal components. And finding the principal components is an interesting problem. It's even stated as an optimization problem to find out. We look at what the PCA approach is. So we want to understand what is the standard PCA approach is. Then we look at a topic called factor analysis. Factor analysis is another interesting topic where it's not driven by the data, but it's driven by some hypothesis. This is the kind of stuff that the social scientists may be interested in. Like a social scientist, a psychologist, might have a hypothesis that the score a student receives in a particular subject is a combination of two inherent attributes for the student. For instance, the student has taken a course on astronomy, and maybe astronomy is the subject might involve mathematical ability. It might also involve verbal ability, because they also talk about different names and words for objects, the celestial equator and all kinds of phrases and all they use. So maybe it involves mathematical ability to know about orbits and ellipses and things like that, and also verbal ability. So, but anyway, the final score a student gets in astronomy might be 85 or 100. And we might say, well, that 85 is a function of two abilities of the student, verbal ability and mathematical ability. So maybe it's 70% mathematical ability and 30% verbal ability. Together gives you that score. A student with a high math ability might score higher. And of course, if these two abilities are kind of poor, then the student overall will score low. So let's say the social scientists wanted to discover what are these two directions. Can you find whether this hypothesis is true, that these are the two abilities that are needed? And he's got all this data of student performance in the course on astronomy. And we'd like to look at that and see whether the student, what kind of abilities the student might have, each student might have. One way to do that would be to look at the exam questions in astronomy and say, look at these three questions, they all involve maths. And look at these three questions, they all involve some kind of, understanding the vocabulary and so on. And say all those questions about math, they all reflect math ability. All those questions that require verbal ability are those other questions. So it divides up the questions into these. And then looks at, is there any correlation between those math questions? Is there any correlation among the verbal questions and so on? And uses that to say, aha, there is some correlations going on here. So we look at correlations to justify our hypothesis and say there are these dimensions, and then we try to figure out what are the weightings of those dimensions and so on. And such an approach is called confirmatory factor analysis. So there's a lot of terminology here. This is interesting to a lot of different communities. Principal component analysis is a standard one. There is confirmatory factor analysis. And then there is also what's called as exploratory factor analysis. The researcher has no idea what are all the dimensions. So one could simply use principal components analysis to tell you, well, these are the main dimensions you have. You have to figure out what those things mean to you. So this is all classic statistics that have been around a long time. So we are here into deep learning. Then we said deep learning has its own approach to these problems. And say, look, after all, in deep learning, we go from mapping to input space to a space of hidden variables. Those are the hidden units. So we have input space to hidden units. And so we have a mapping going on here. And it depends on the architecture. And what kind of interpretation can we associate with that, with that latent space, we call it. All right, so latent spaces, and we can argue that the latent space representation is a generalization of the PCA representation, where you are figuring out how many dimensions you want. Are you interested in only 1 or 2 or 30 or 40 and so on? So we can think of the hidden representation as a generalization of the idea of PCA. So we're going to look at PCA, we're going to look at factor analysis, we're going to look at latent representations, and linear factor models come into play. And those are exactly what neural networks do, where we have a simple linear transformation. The input is multiplied by matrix X or matrix W to give the next layer. So we think of it as a linear transformation. We're just multiplying each input by some value, adding them all up. That's called a linear transformation. So we will look at such linear transformations. And then we say that this basic idea, simply multiplying the inputs by some weights and adding them up, is the basis for much more complicated algorithms. And you can do very sophisticated stuff to capturing the distribution of the data. And just like we had linear classifiers in linear regression, where we map inputs to classes or inputs to values in classification and regression. And then we say, well, such simple ideas can be made more powerful if we allow for those inputs to be not just raw data, but some functions of the raw data, which are called as basis functions. Then you can create arbitrary variations, even though you're limiting yourself to linear models. You're going to get lots of nonlinearity and make it much more powerful. Just like that, linear factor models are simple factor models. They again can be generalized to all kinds of things like autoencoders and generative models and so on. So this is, keep that in mind why we want to study this topic. On the one hand, it relates to very simple ideas that you might have heard of. And then on the other hand, it relates to very complex ideas that we will be speaking of, okay? So let's take up our slides. Okay, so here we have our slides, linear factor models. All right, so I've given you the preamble for what today's lecture on linear factor models is about. So this is what I was mentioning earlier on. I'm just going to actually show you the slide. The slide at the top left is taken by an amateur astronomer, not by a NASA Hubble telescope or anything. I mean, they get these kinds of pictures as well. This was just taken by an amateur astronomer. He has a camera in his backyard, and he pointed his camera towards a particular constellation that's shown on the top right here. It's called the Andromeda constellation. And if you peer through that Andromeda constellation, you see this galaxy over there. Galaxy, it's called the M31 galaxy. And that's the one that is 2.1 million light years away. And that's the one that's heading on a collision course with the Milky Way. That's the one that's coming towards us. It's the closest galaxy to the Milky Way of all the galaxies in the universe. And in about 4 billion years, well, after we are going to be worried about the COVID and all that, right? 4 billion years from now. We won't feel much from the mashup. There is so much empty space between the stars of both galaxies that few, if any, will notice. So they're just going to go through each other. All right. But what was interesting to me, he just was posting these photographs, beautiful photographs he's taking. And I said, wow, that looks like principal components analysis. Not quite, but what it is that galaxy could have had all those stars kind of, uniformly distributed over a sphere. Instead of that, it's all largely flat. And like a pancake, we can refer to these as pancakes. It's like a pancake in three-dimensional space. And that's the nature of data. I mean, we are not talking about physical objects. We're talking about data points. So data points are also in a high-dimensional space. This is only three-dimensional space here. We deal with very large dimensional spaces. So every point is a particular instance of that assignment to those set of input values. And they're also structured like this. So that's kind of an interesting point, I thought. So anyway, that's a motivating thing. This is the Andromeda constellation. Why is it called Andromeda? This is the Greek goddess, I think, Andromeda. So you can see the form of the Andromeda in these stars here. Okay, that's why they called it Andromeda. Anyway, so we're going to look at PCA and factor analysis that go about trying to say, well, we really don't need 3 dimensions for all of this kind of data. We could just show it as a flat pancake. We could just figure out where is the pancake, what is the linear transformation from 3 to 2 dimensions, and show all the stars on the 2 dimensions. Of course, we'll miss a lot of things that were on the that were not on the pancake, but basically they largely capture the nature of the data. So the topics we're going to look at here are principal components analysis, factor analysis, and then into these deep learning methods of linear factor models. And we say those are generalizations of principal components analysis and factor analysis. And there are so many other variants of linear factor models that people have used in the deep learning community. One of these is called independent component analysis. This is to take complicated signals that are mixtures of lots of things and separate them out. You know, the classic example of independent component analysis is to have a microphone in which you have many people talking at the same time, like a cocktail party. And you want to focus on one of the speakers rather than listen to all the cacophony. So you want to look at the sounds that are independent of each other and extract them out. That approach uses some version of linear factor models. There is one more application called slow feature analysis. This is when you're looking at, let's say, images that are rapidly moving videos. And certain things move fast from frame to frame, like details of the background and so on might be changing rapidly from frame to frame, but an object moving from frame to frame, it's still there. It's not changing so rapidly. So that's kind of, some features change rapidly, some features change slowly. So how do we differentiate between these? And again, these linear factor models are used. And some methods of sparse coding. This is, you want to take advantage of the sparsity of the space. So that's yet another approach to compress the data. And finally, we come back to a manifold interpretation of the PCA. That is, manifold means like that pancake. A pancake is a manifold, particular surface. It need not be flat. It could be a two-dimensional sheet, a rubber sheet, 3 dimensions. So data is not all over the space. It's only on the sheet. It's called a manifold. So these are all kind of mathematical topics, but they form the basis for some of the more interesting research in deep learning. So here is an example of principal components analysis. This happens to be data that comes from some area of biology, like bioinformatics. So we have a 3-dimensional world on the left. We have something about the gene 1, gene 2, and gene 3. It's 3-dimensional data. So you have some data of DNA, gene 1, gene 2, and gene 3. There's a particular point here. There happens to be some classes maybe corresponding to different categories of species or something. And they're all kind of lying on this particular 2-dimensional plane here. They're not all over the 3-dimensional space. They're kind of on this plane. And we can say that particular plane has dimensions PC1 and PC2, only 2 dimensions. So we can say, well, we don't need to retain the values in 3-dimensional space. If we can only find this particular PC1 and PC2, we can show all of the data just on this 2-dimensional plane. That's called principal components analysis, which takes you from the original data space to the component space, where we have a plot of PC1 and PC2. And the 4 categories are shown almost more clear in a 2-dimensional space. So we are kind of discarding 1 dimension and getting another dimension. Also, only thing is when we go from this dimension to the lower dimension, we need to do a linear transformation, which is to take the values along the 3 dimensions and we need to multiply them by some values and again add them to give you values along the 2 dimensions, and that gives you this. So this is what principal component analysis does. It figures out what the linear transformations are. Here is one more example of principal components analysis. On the left side is 2-dimensional data. These are some data points we have, gene 1, gene 2. So something was measured, and we have data like this scattered all over. We can ask the question, can we represent all of this data in 1 dimension? Can one value capture it instead of 2? Well, they say, okay, we can do principal components analysis that says, well, look, along this particular straight line, among all possible straight lines, the data seems to have the highest amount of variance. That is, if you plot all these, project all these points, the spread of the points is largest here as opposed to any other direction. And it's going through the mean of the data, somewhere in the middle here. Right? So then we refer to this particular direction as the PCA first dimension, principal component analysis first dimension. That's how we've labeled it here. And we take the perpendicular direction to it as PCA second direction. So if you wanted only 1 direction, then we have it. If you want 2, we take that and value orthogonal to it. So that's PC1 and PC2. This again is PCA from 3 to 2 dimensions. So how do we find those directions? There are all kinds of algorithms available. This is a machine learning solution based purely on linear algebra. It says given x1 through xm, we have m points in n-dimensional space, Rn. We want to represent it using RL, L is less than n. So take it from n-dimensional space to L-dimensional space, lower dimensional space. So to do that, for point xi, that is one of these points, find a code vector Ci in RL. So we need to encode each point in this lower dimensional space. X becomes a C. So we're saying we need an encoder. We could say f of x equal to c. It takes x and gives you a c. So you can map from high dimensional space to low dimensional space, but it'd be nice to have a decoder also, which is given the mapping f of x, can you find a decoder G that operates on the encoded version and gives you back the original? So we don't want to find arbitrary mappings. We want something that makes sense. It's possible to recover to some extent. We're saying approximately equal to, because we had lost some information when we went from high dimensional to low dimensional space. So we would like to approximately come back. It turns out one decoding function, what is this G function, is GFC equal to DC. So we can take the encoded version multiplied by a matrix D to get the original value back. And this D is a matrix with L mutually orthogonal columns to minimize distance between X and its reconstruction. So there is X and then its reconstruction is R of X. So it says a reconstruction can be obtained by taking the transpose of this matrix and then multiplying by D, it gives you back. So this is all matrix manipulation. So that's a possible decoding function. So we can say C star, the ideal coding is one that minimizes the difference between X and its reconstruction. So the coding should be such that the reconstruction should be as close to the original as possible. That's what this argument over all possible C's is, this C star. And what is the D star? That's the ideal D is one that says over all possible D's, it minimizes X minus R of X squared, the difference between these two. I guess these two are related to each other. And this is taking the sum of squares for all these dimensions. So we get this back. And so if your problem is stated, it's all in algebraic terms. The solution D is the L eigenvectors of the design matrix X. So this X is belongs to Rmn. So from the m-dimensional space, this is M is the M samples, and N is the dimensionality of that space. So it says you take the design matrix whose rows correspond to the data columns correspond to the values, the features. And we say we compute the L eigenvectors of the design matrix corresponding to the largest L eigenvalues. So, that's all it is. Just get me a design matrix and find some numerical routine to give you eigenvalues and eigenvectors, and you say however many dimensions you want, you can find it. That's it. That's simple. There is nothing fancy here about finding those dimensions that we just saw from 3 to 2 and 2 to 1 and so on. Can all be done like this. So that's pure linear algebra. That's pure PCA. Anyway, let's go to this other topic, which is again, we relate all these things together. So confirmatory factor analysis is a researcher has a hypothesis and wants to confirm that hypothesis. So he uses factor analysis. It's a technique for identifying which underlying factors are measured by a much larger number of observed variables. So we're talking about scores in an exam. And the underlying factors are difficult to measure. So there could be like IQ, depression, extraversion. So the researcher wants to see whether what is observed is a performance on actual tasks. And can we give some support to these kinds of hypotheses? For instance, here is a questionnaire. Questions 1 through 9 are questions that actually students answer. And the researcher has an hypothesis that first 3 questions relate to numeric IQ. Next 3 questions relate to spatial IQ. And the last 3 questions refer to verbal IQ. And wants to confirm whether this is true. And the way it is done is you capture the data, like you have a whole set of students who have answered all these questions and who have got scores, and then this researcher says, well, I'm going to just look at these as groups of 3 and say whether questions 1, 2, and 3 are correlated. And these are question 1, question 2, question 3. This is question 1, question 2, question 3. And the entry here has a high value close to 1, if they are correlated. So it's computing the Pearson correlation value, right? One value goes up, the other one value goes up, like that. So these 3 being numeric, they should be highly correlated. And the researcher says, aha, these 3 are all highly correlated. Similarly, the next 3 are all correlated over here. And finally, the last 3 are all correlated over here. But when we look at the correlation between question 1 and question 4, that's a low correlation, 0, 4 there, which means these questions are numeric questions. They're correlated with each other, but they're not correlated with spatial. They're not correlated with verbal. So this is how a social scientist would say that even though there are 9 questions involved, there are only 3 underlying factors and corresponding to, I don't know, whatever it is, IQ, depression, extroversion, or in this case, it's numeric, spatial, and verbal. So essentially, those are the values. That's how the data is distributed. And it confirms the researcher's hypothesis. If these correlations don't show up as nicely, then of course, it doesn't confirm that the hypothesis is true. So anyway, that's what they do in confirmatory factor analysis. And the other thing is exploratory factor analysis, when the researcher has no clue as to even how many factors are represented by the data. So in exploratory factor analysis, let's say this is another example that the psychologists have a hypothesis there are 2 kinds of latent intelligence: verbal factor F1 and mathematical factor F2. And the evidence for the hypothesis sought in the examination scores from 6 academic fields. Astronomy is one of them. And there are 1,000 students who are taking this course. So the observable variables are x1 through x6 corresponding to 6 subjects, and the means are mu1 through mu6. So we say that the value xi minus mu I for each subject is a combination of f1 and f2 plus an error epsilon. So we have li1 f1, li2 f2. We refer to these li1 and li2 as loadings. So for that subject, so there are these two factors showing up in all the 6 exams. And in matrix form, x minus mu in all the courses together is L times F. These are matrices, L times F plus epsilon. So x is p by n, all right, corresponds to 6 subjects and n students. And L is p by k and F is k by n. So values of L, mu, and variances of errors must be estimated from the data. So again, we have to do some optimization of the kind we just talked about. And well, you know, coming out of all of this would be saying astronomy has a loading, which is 10F1 and 6F2. All right, F1 and F2 corresponding to the verbal and mathematical factors. And verbal is getting a loading of 10, and the other one is getting a loading of 6, right? So this is again the kind of thing where we are reducing from 6-dimensional space to a 2-dimensional space, saying that there is an explanation given, which is the kind of thing we want to do in deep learning. We're saying we are trying to find underlying factors to this data. What is meant by a face, right? We can't just describe it in ordinary terms. A face consists of eyes, nose, mouth. There's much more to it, much more variability. And what is the essence of it is what deep learning tries to find. So factor analysis is a term that used in many ways. The method to describe variability among observed correlated variables in terms of a lower number of latent variables called factors. And the observed variables are modeled as a linear combination of the latent factors plus error terms. That's what we just saw. That's a linear combination with error terms. So is there a difference between PCA and factor analysis? This is kind of interesting terminology. Both are data reduction techniques. Both involve choosing components or factors, but there are fundamental differences between them. PCA is a linear combination of variables. Factor analysis is a measurement model of a latent variable. Right, so let's take a look at that a bit more. PCA is a more basic version of it. So we can say we're going to do it, look at factor analysis, and PCA is a basic version. This is an interesting diagram which shows side by side PCA on the left side and factor analysis on the right side. On the left side, we see we have observed variables y1 through y4, and these variables are multiplied by w1 through w4 to give a single value c. So we can say that these 4 measured variables are measured into a single component c. So the model is set up as c equal to w1 y1 plus w2 y2 plus w3 y3 plus w4 y4. In factor analysis, we have set a variables y1 through y4. But we say that these observations are caused by a factor f. This is like that verbal ability. So the observed values on the subjects, some combination of b1, b2, b3, b4, like y1 equal to b1 times f plus some u1. There is also some variance contributed. It's not like strictly that value, but there is some statistical variability. So this, we say that the model is set up as regression equations, y1, y2, y3, y4. Right? So it's a regression of observed value. So the topic would be to figure out what is the value of f, right? And so this is the difference between principal component analysis and factor analysis. Here again, we're trying to figure out the weights w1, w2, w3, w4. And here we are trying to figure out the values y1, y2, y3, y4 again are observed values. And so there is a latent factor, and the latent factor has some weights b1, b2, b3, b4. And there is u1, u2, u3, u4. So we need to figure out all these parameters in factor analysis. So in a way, this kind of captures something that are extremely similar to each other, but there is still differences between the two. Okay, now we get back into the mainstream of deep learning. Once we remember what is PCA, what is factor analysis, so we'll come back to linear factor models. So many research frontiers in deep learning involves building a probabilistic model of the input. We're saying here is a bunch of X's, which are all these images, and we have to construct a model of them, probabilistic model. And such a model can be used with probabilistic inference to predict any variables given any other variables. We can use it to predict a value of another variable. But typically we want to know the distribution we can have a conditional probability, or we can have a marginal probability. We could infer things like that. Or we can generate a sample from it, saying here is a sample from this distribution, which is a true member of that distribution. So many of these models have latent variables also in them, H. And we can write P model of X is equal to expected value of P model of X given H. What is this? That can be obtained by a simple Bayes rule application. We can say the distribution of all the samples in this model is the expected value of the conditional distribution of X given a set of hidden variables. Now recall, what are the hidden variables? We have an input. This is the MNIST actually, and goes through a layer W1 times the matrix W1 plus a bias B1 plus, in this case, ReLU is the activation function. Right? So we are able to generate some set of values here, 1 by 200 values here. And that again is input to another set of weights and then another bias. And we get these actual values here, and which are then subjected to softmax, which is going to convert them into values between 0 and 1 as probabilities. So they add up to 1. One of them has got a high probability corresponding to 7, I suppose. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 7 has a probability 0.7. And we can always threshold it, saying that corresponds to a 7. And here is the one hot vector representation, where only one of them is 1, rest are all zeros. We might be using a cross entropy to backpropagate to figure out the values of these weights and so on. So this is what happens in a standard feed-forward linear deep neural network. But the point of putting this up is that the distribution of the X's, which is all of these images in this input of size 1784. It's a 1784 dimensional space, which is 28 by 28 image. It is modeled by a set of values H here. So given H, the distribution of the X is given by P of model X given H. It's conditional distribution. And its average, E of H is just an average over all values of H. So there is the relationship. So we're saying the distribution of X need not be in the original X space. It is a conditional space. So given the H, the distribution of X, which has got fewer parameters than over the high dimensional X space, than this lower dimensional, like we went from 1784 to 200, like that. So much of deep learning involves building a probabilistic model, and many models, we just saw these two statements earlier on. And distributed representations based on latent variables can have all the advantages of representation learning with deep feed-forward and recurrent networks. So we can have all these complicated models and have simple distributions. So linear factor models, they are the form shown in this equation at the bottom. Defined use a stochastic linear decoder function. It generates X by adding noise to a linear transformation of it. So your observation X is given by a W times H, the kind of thing we just saw. The matrix is multiplying a set of hidden values, right? The hidden values, of course, can be obtained from a previous level by, so we're saying X itself is obtained from H by WH plus B, some bias, and then noise. So that is the essence of the model, is the mapping between H and X. So a linear factor model describes a data generating process where we first have the explanatory factors H have a prior distribution. So PFX is a factorial distribution. And then next we sample the real valued observable variables given the noise, X is equal to WH plus B plus noise. So we get H from a standard simple distribution and noise is Gaussian. And this way you can generate data from the hidden values. Where we are heading towards is, again, keep in mind that pancake. You have a point on the pancake, which is H. So we can get its three-dimensional representation by multiplying it by appropriate matrix and with some noise added, we can come back from H to X. So the graphical representation, those of you who are exposed to probabilistic graphical models know what this kind of a diagram is. We have X is at the bottom, X's. These are the values of X's. And those X's are all dependent on the H's above. We refer to this as parent-child variables. So we're saying the observed values are being generated by the hidden values. So again, this represents X is equal to WH plus B plus noise. So that's the matrix multiplication. So the essential linear factor model is this diagram and this equation. This is saying H has a prior distribution PFH. With PFH is a product. It's a very simple idea that these are all independent. H1, H2, H3 are all independent. So we can multiply those three priors to get the joint for H. And then X is obtained by the matrix multiplication of W times the H values plus B plus some noise. So this is the linear factor model. And the special cases of these above equations are probabilistic PCA, factor analysis, other linear factor models like the kind that we'll see later. And they differ in the choices about the form of noise and prior over the latent variables H before observing X. So factor analysis and probabilistic PCA will come up next. So if we use prior PFH is a unit variance Gaussian, all right, then Xi are conditionally independent given H. And noise from the Gaussian with covariance matrix has this form. It's a diagonal matrix for the variances. And the latent variables capture dependencies between the Xi. It can be shown that X is multivariate Gaussian. So in factor analysis, we can show that this X is assumed to be multivariate Gaussian. If we're using exactly this model, some W's are generating the X's from the H's. So the basic idea we saw earlier on is being explained by this set of equations here. Similarly, what about probabilistic PCA? The PCA we saw earlier on. This is a slightly modified factor analysis model. And it is saying X is again normally distributed with these weights W, the sigma squared I, the bias B, or equivalently X is equal to WH plus B plus sigma Z, where Z is Gaussian noise. And iterative expectation maximization can be used to estimate W and sigma squared. And probabilistic PCA becomes PCA as sigma tends to 0. Huh. So what we are saying is, we started out by talking about PCA, simple idea of finding the principal components. Then we're coming up with something more fancier with terms of these equations and this graphical model. And we simply say, well, if you choose the parameters for this model in some simpler way, you're going to end up with something called probabilistic PCA, a version of which is standard PCA. And we also showed in the previous slides also some standard factor analysis. So the main message to go away with, even if the equations look a little complicated, is that if you say, hey, I know what PCA is, all right, this says neural networks can be made to do exactly what you want, PCA, or we can do more fancy things like probabilistic PCA, or we can do something, factor analysis if you want to do. So all of this can be done with a neural network. And then now we move on to other variety of things, independent component analysis, which can be used to separate observed signal into underlying independent signals that are scaled and added together to form the observed data. So this reminds you of maybe Fourier analysis, that the observed signal, which might be a complicated signal, you can say that's just a combination of a bunch of basic signals, the sinusoids added together with some weights is giving you the signal. The same kind of idea here, saying there might be underlying signals, but then they are independent. So what if I have components that are independent and adding up? That is two people speaking at the same time. Like a lot of our political shows, right? There's all these pundits on whatever topic, they're shouting at each other independently. So you're getting these two signals simultaneously and you're listening to two speeches simultaneously, but they're independent. Independent component analysis is, given the signal of two people speaking at the same time, can you separate them out into two? So that's what's being illustrated here. So we have three examples of mixed signals on the first diagram here. Independent component analysis, I'll take a look at the signal. It's got an underlying signal here, and then there is some noise on top of it. So maybe that should be just, this is the underlying signal, looks like that. And similarly, this blue one has this underlying signal, the true source is like that. And the mixed signal here is a combination of these two here. And the combination of these two, true source, is also looking like that. So basically, we're talking about separating it out, the mixed signals. Like the first one is a mixed signal, getting the true signal, mixed signal, true signal, mixed signal here, true signal here. Because the last one is just noise. So the other one is a cocktail party problem. Speech signals of people talking simultaneously are separated. We have three people talking simultaneously. The algorithm separates the voice. There's a deep neural network here. And there are three signals coming out here. Each voice is compared with the listener's neural signals. The closest match is the one that is amplified. I suppose the listener here is choosing one over the other, saying I want this or that. And that's what's being produced. An interesting problem of separating out signals. This is an interesting slide. You might want to know this irrespective of all this lecture. This gives you an example that independence and no covariance are not one and the same. So signals are intended to be fully independent rather than merely decorrelated from each other. So something to keep in mind is independence is stronger than zero covariance. So if you have two variables that are not correlated, does it mean they are independent? It says the answer is no. Independence is stronger than zero covariance. Really? So here is an example. It's a contrived example, but it's an interesting one. Supposing we have a variable x whose values go from -1 to +1, 0 in the middle, and we sample from maybe a uniform distribution between -1 to +1, we get a value, let's say 0.5 or something. Supposing we have another variable s, which is binary valued, which is either 0 or 1, and each with probability 0.5. So it's 1 with probability 0.5 and 0 with probability 0.5. So it's just like tossing a coin. Did you get head or tail? So that's the value of S. So X is some value like you got, like 0.5 is your current value. And maybe this value is 0. So we say let Y is equal to S of X, S times X. So it says take that 0.5 and multiply it by 0 and your value is 0. So your Y value is 0. S value is 0. X value is 0.5. So we're saying clearly X and Y are not independent. Y depends on X and Y. So X and Y are not dependent. It's Y is generated from X. So we take the value of X and we generate the value. So we say that Y and X are dependent on each other. They're dependent. But X and Y have 0 covariance. This says, does X have any influence when X goes up or down? Does Y go up or down? It says no, because that's getting modified by this value between 0 and 1. So we end up saying X and Y are not correlated, but X and Y are not independent. So this says, if you find two variables are not correlated, doesn't mean they're independent of each other. So it's a very interesting observation that independence is a stronger requirement than covariance. It's a very interesting concept because these issues come up all over. So for this kind of independent component analysis, prior PFH is fixed ahead of time, and the model deterministically generates X, and we use change of variables to determine P of X when a derivative is being taken, and learning proceeds using maximum likelihood. And by choosing independent PFH, we can recover underlying factors that are close to independent and used to recover how low-level signals are mixed with each other. So this is saying that same equation can be used for this problem of independent component analysis. And some examples are shown here about signals and recovered signals and choice of PFH to be non-Gaussian. So anyway, this applies to those who might be specifically working on a problem like this, independent component analysis. Slow feature analysis is another topic. And this is again a linear factor model. And this is an example showing a zebra in a video. It is running from right to left, I suppose. The stripes of the zebra change dramatically from frame to frame. Pixel values, black and white and black and white and black and white, change a lot. But the zebra may be present in every one of the frames. So we say some pixels are rapidly changing, that is the black and white pixels. But the presence or absence of zebra is not changing that much, remaining the same. So this is about modeling this kind of behavior. And this can be used with a linear model, linear factor model with an appropriate loss function. Anyway, this is just a list of topics. I'm not planning to really go over every one of them. So it's a huge involvement of time to go through every one of them. So sparse coding is a linear factor model. So those of you who are interested in it might want to be looking at it. That's yet again a linear factor model. And the definition of what is meant by sparse coding and so on. The last part is manifold interpretation of PCA. Linear factor models, including PCA and factor analysis, can be interpreted as learning a manifold. Probabilistic PCA learns a flat pancake of high probability. So flat Gaussian with low dimensional manifold. So shows upper half of pancake above the manifold plane, which goes through its middle, and variance of orthogonal manifold is small as noise, and while other variances are large, correspond to the signal. So the upper direction is small variance and the other one is large variance. So this is a manifold, and so the manifold interpretation applies not just to PCA, but to any linear autoencoder that learns matrices W and V. And so this analysis of figuring it out, which all it involves is the matrices W and V, would involve equations like this and some optimization. Okay, I didn't give all the solution to that problem, but essentially we are saying that whatever be the data, where is some continuous data, they're going to be lying on some manifold, and how to figure out that manifold. Just like in PCA, we're trying to figure out the maximum variance. We're trying to figure out these lower dimensional manifolds can be done. Some optimization algorithms. So linear factor models are the simplest generative models because you can generate X from the H's. So you're mapping your X's to the H's, and from H's, you're getting back X's. So you can generate sampling from H, gives you samples in X. Simplest models are linear representation data. And there is an analogy between linear classifiers and linear factor models. So linear classifier models are extended to deep feed-forward networks. So we know that simple ideas like logistic regression are simple classifiers, linear classifiers, but we start there and we generalize it and get deep feed-forward networks. Similarly, linear factor models are extended to autoencoder networks and deep probabilistic models. They perform the same tasks, but with much more powerful and flexible model family. So the generative models that are going to be coming up can be thought of as more complex versions of the same linear factor models, which involves a fairly simple PGM and a fairly simple set of equations. Okay, so that's the lecture for today, and happy to take any questions you might have. Okay, so today, Monday, the 20th of April, was linear factor models, chapter 13. So we're going to go a little bit faster. We went very slow on applications, natural language processing. We spent 2 weeks on that. This was just one lecture on this topic. Wednesday's lecture is going to be on autoencoders. I mentioned autoencoder a few times. So we look at it formally in a way. That's a little bit bigger topic. I may need a little bit more than one lecture, but let's see how it goes on Wednesday. So you may want to look up chapter 14. There are something like 20 chapters or so in the deep learning book. So we have another 6 to go. And I've added 1 or 2 more on GANs as a chapter of its own. So we'll cover all of it. We have plenty of time. So that's it. Okay. I'm going to stop the recording now.